Hello, welcome to another physics lesson. Today we'll be looking at nuclear energy. We are going to see what nuclear energy is. We will mention and define the two types of reactions that produce nuclear energy. We will state the Einstein mass energy equation. We'll explain chain reaction, and then we'll describe the operation of the nuclear power plant. So, come along and let's learn something exciting in physics. Recall that we already said under another topic, atomic physics, the video is right on this channel. We said that nucleons in the nucleus are held together by powerful nuclear forces. Just by way of recap, what are the nucleons? The nucleons are the particles that we have in the nucleus of an atom. And those are the protons and the neutrons. Now, an incredible amount of energy is required to pull these nucleons apart. As small as the atom is, the nucleons in the atom have a very, very massive nuclear force keeping them together. Because even though the protons are there in the nucleus, which are all positively charged, ordinarily they should have been repelled. They should have repelled each other. But this nuclear energy, this nuclear force holds them together. This energy is quite enormous, actually over 1 million times more than that required to remove electrons from an atom. So before you can now separate these nucleons, you need a massive amount of energy. So the massive amount of energy that could be used for other purposes can therefore be got from the nucleus of an atom. This energy that is got from the nucleus of an atom is what is called nuclear energy. And there are two types of reactions that can produce nuclear energy. We have the nuclear fission and the nuclear fusion. So let's look at them one after the other. Let's start by looking at nuclear fission. Nuclear fission is the splitting up of the nucleus of a heavy element into two other elements with the release of a high amount of energy. So you have an element that is heavy, like uranium, much heavy. Uranium-235, atomic mass 235, that is quite a lot. Now, in a nuclear fission process, this uranium can be split into krypton and barium, which have less atomic masses. Now, this energy also releases a very high amount of energy. In this kind of situation also, the krypton and the barium that are formed from the uranium are called daughter nuclei. So when you split a heavy nucleus into two other nuclei, the 2 or 3 other nuclei that you have are called daughter nuclei. Now, experiments have shown that the total mass of the daughter nuclei that you have are usually less than the mass of the parent nuclei. They're usually less than the mass of the parent nuclei. So, what then is responsible for this difference? The thing responsible for this difference is what we call mass defect. Mass defect. The mass defect you get is the measure of the nuclear energy released. So, in other words, I'm saying that when we split uranium-235, that is quite heavy, into two daughter nuclei, krypton and barium, if we add up the two masses of the krypton and barium, it will still be less than the mass of uranium. Now, that difference is what results in the nuclear energy you are able to get from that reaction, from that nuclear fission reaction. Now, that energy is given by E equals delta m c squared, where delta m is the mass defect, as I said, the difference in masses of the product and the reactant size, and then c is the speed of light. And this equation is what is called the Einstein mass energy equation. On your screen here, you have pictures of a nuclear fission process. You can look at the different nuclear equations that we have there on the left part, the A of that picture. we have uranium-235 splitting up in different instances to form different elements. The one I use in my analogy, the one for barium and krypton, is what we have as the last one there. Now, this nuclear fission process usually occurs when something triggers that split of the heavy nuclei. Something will trigger that split, usually a neutron. A neutron. At times it may be a proton, it might be an electron, it might even be some kind of gamma ray or electromagnetic wave that triggers it, but usually it's a neutron. So when the uranium nucleus is bombarded with a neutron, it can split that uranium nuclei into daughter nuclei. We have different daughter nuclei that can be formed there. Now, then just to bring the picture clearer home, we have this other diagram here. You can see the motion of the neutron is going to hit the uranium. After hitting the uranium begins to split up and it forms the daughter nuclei that you have. Now let's look at the second type of nuclear reaction. That is nuclear fusion. As the name implies, when you hear fuse means things coming together to form one, things coming together to become one. So fusion is the joining together of two or more light nuclei to form a heavy nucleus. That also releases a large amount of energy. A very good example of where we have deuterium and tritium forming helium. Those are isotopes of hydrogen forming helium. If you do not know what isotopes are, please see the video on atomic physics that was explained in that video. For fusion to take place, very high temperature is required because the repulsive forces that you will have between nuclei coming together is quite heavy. So you need a very high amount of temperature to break that repulsive force. That is why fusion is very difficult to actualize in practice. But then we still have instances where fusion takes place in nature, for instance, in the sun and in stars. Materials that can withstand this kind of temperature are very hard to come by. Here we have an example or an equation of what nuclear fusion looks like. We have also here helium and nitrogen forming oxygen and then releasing an isotope of hydrogen also in the process. Helium plus nitrogen forming oxygen and then releasing an isotope of hydrogen. And as I said earlier, in the sun we have deuterium and tritium coming together to form helium. So that is what we have in the second diagram. You can see the deuterium and the tritium. The arrows that are taking them in mean that they are coming together. They form helium, release a very high amount of energy, and then they also release a neutron in that reaction. Even though it is very difficult to fulfill, nuclear fusion actually has some advantages over nuclear fission. Nuclear fusion produces less dangerous byproducts. For instance, when deuterium and tritium come together to form helium, helium is non-radioactive. It is not a dangerous byproduct. Unlike you trying to split up uranium to form krypton and barium, those are radioactive in themselves. The second advantage is that raw materials required for fusion are cheaply and readily available. I mean, we can get hydrogen easily from electrolysis of water. Seawater, we get hydrogen. Hydrogen is a component of water. Do not forget that, H2O. So we can get hydrogen readily. Fusion is also easily achieved with lightest elements. Hydrogen is a very light element. So because of that, we can overcome the repulsion easily. Then, very large amount of energies can also be obtained from fusion. An example is what we have from the sun. The simple fusion of tritium and deuterium gives us that massive energy that the sun has. Another example is what we have in the hydrogen bomb. Very large amount of energies can be obtained from fusion. Let's now look at some non-dangerous uses of nuclear energy. We are trying to make the world a better place, so we don't want to look at those dangerous uses that we have, like nuclear bombs and all that. No, we are focusing on the non-dangerous uses, the good uses of nuclear energy. Nuclear energy can be used to produce electric power in nuclear power plants. I mean, there are many nuclear power plants around. Nuclear energy is also used for radiotherapy in medicine. That's what is used to view cancerous cells, for instance. Radioisotopes from nuclear plants are also used as tracers and preservatives. Tracers are like it's used in medical diagnostics, where you send an iodine tracer, for instance, into the body to see which of the cells would react adversely to that. Now, spacecraft, ships, and submarines can be powered by nuclear energy also. I mean, we can build nuclear reactors to power all of these things. Those are very good uses of nuclear energy. Let's look at chain reactions and the nuclear reactor. Chain reactions are reactions that stem from a repeated or a continuous nuclear fission process. Fission, splitting up. So chain reaction stems from nuclear fission. It is a multiplying and self-maintaining reaction that is set up when uranium-235 is bombarded by a slow neutron. As I said earlier, to split up the uranium, you bombard it with a neutron. When that happens, uranium is split into krypton and barium. Now, that reaction itself also releases neutrons. It releases additional neutrons. The neutrons that are released will also move to strike other uranium atoms that may be nearby, and then those other uranium atoms too will split again, and then you have that process continuing like that, and then that is what we call a chain reaction. So this is a process used in nuclear power plants to generate electricity. In a nuclear reactor, for instance, we control the process. We use uranium as a fuel. We now control the process somehow so that the reaction doesn't get out of hand. But it will take a very longer period so that we can have massive amount of energy from it, which is then converted to nuclear energy. So in a nuclear reactor, the process is controlled so that the heat generated from the chain reaction is generated over a longer period. Now, the heat generated from this chain reaction is used to heat water. A nuclear reactor, you see the diagram shortly, has a water chamber there. So the heat generated heats up that water. Now, when the water is heated up, it produces steam. Now, this steam is what is used to drive steam turbines. Steam turbines are attached to a generator, and the generator generates electrical energy. If you remember our lesson on EM induction, electromagnetic induction, we use motion generators to generate electrical energy. This is then sent to a transformer to step it up to the correct voltage. The entire aspect of a generator and how a generator creates electrical energy and the operation of the transformer are also in different videos on this channel also. You can do good to refer to them. Now, in the nuclear reactor, we use uranium as the fuel, as I said earlier. So uranium is used as fuel. Graphite is used as a moderator. At times it may be water. Some nuclear reactors actually use water as a moderator. What the moderator does is that it absorbs some of the kinetic energy of the neutrons so that the neutrons get slowed down. Now, slow neutrons are more easily absorbed by uranium-235. That's why we need to slow down the neutrons so that uranium can absorb them, and then the chain reaction can begin. Now, the nuclear reactor also has control rods. These control rods are made of boron or cadmium, and the function of the control rods is to absorb neutrons and take them out of the reaction completely. So when the chain reaction is going on and the neutrons being produced are beginning to get too much. They are beginning to get too much, such that they can begin to create an avalanche that will be out of control. The control rod just absorbs some neutrons and takes them out of the equation. Now, this is the function of the control. So the main parts of a nuclear power plant, therefore, we have the fuel, the uranium fuel, which is very important. We have the graphite, which is a moderator. Then we have the control rods, which are made of boron or cadmium. And then, of course, a very key part also will be the chamber, the casing, that all of these things are inside, so that radiation doesn't seep out. In most cases, the casing is made of concrete. Let's see a pictorial representation of chain reaction. Here we have a neutron bombarding a uranium-235. That uranium forms krypton and barium. Krypton and barium, in the process, 3 other neutrons or 2 other neutrons in addition to the initial neutron, making 3, are also released. So each of those other neutrons will strike another uranium-235 atom. Those ones will split up again, each of them releasing 3 neutrons also. Those 3 neutrons will also strike other uranium atoms that you have in the chamber. So you see that the number of neutrons being produced is getting higher and higher. That is why we need the control rods to take out some of them at a certain point. So this is a simple demonstration of a nuclear reaction. Let us wrap this up by looking at a diagram of the nuclear reactor itself. As I said, it has a containment structure, so something that will contain radiation. It is made of concrete in most cases. Then we have the reactor vessel. The reactor vessel is where we have the uranium fuel, where we have the fuel rods. The fuel rods are those tiny rectangular lines you see in the reactor vessel. Those are the fuel rods. Inside there also we have the moderator and we have control rods. Now, the heat generated, as I said, is passed to water. Then the water is heated to produce steam. That's why you can see a steam generator there. The steam generator is attached to a turbine. A turbine is attached to a generator. The generator now produces the electrical energy. Then we send the electrical energy to a transformer, which will now step up the energy produced to the required voltage for onward transmission to cities or to the consumers of the electrical energy. So this is the end of today's lesson. I hope that this gives you a better understanding of how nuclear fission and nuclear fusion processes occur, and the good of nuclear energy, especially as it relates with producing electrical energy as in the nuclear reactor. Thank you for listening. I hope that this gives you a better understanding, and I hope to see you in some other video some other time. Please, there are videos on different topics, very short videos on different topics in physics right on this YouTube channel. David Oluwadara is the YouTube name. Please feel free to check on any of them. Subscribe to the YouTube channel to get notifications when new videos are uploaded. Thank you.